Hello friends, you are welcome to my YouTube channel Nepcam Guru. Today I am going to discuss about the basic MCQs in volumetric analysis. If you are in class 12, if you are reading class 12 science and taking chemistry as a subject, then you can prepare volumetric analysis MCQs, basic MCQs from my these videos. So all of you are most welcome to my YouTube channel. So today let's start about the basic MCQs in volumetric analysis. Let's go on number one, first number. In very first number, we will be describing about the one of the important MCQ of volumetric analysis, that is, which of the following method of analysis is quantitative? Which of the following method? Which of the following method is not a quantitative analysis? Not a quantitative analysis. Which of the following method is not a quantitative analysis? A number. Which out of four options, which of the following is not a quantitative analysis? So I'm giving the options here. First number is gravimetric analysis. Gravimetric analysis. Gravimetric analysis. And number B is volumetric analysis. Volumetric analysis. And similarly, in number C we have option detection of radical in salt. Detection of radical in salt. Detection of radical in salt. Number D is we have number D is acidimetry. So let's see option here. This is the very first objective questions, multiple choice questions. So let's see here. Which of the following method is not a quantitative analysis? Here we have gravimetric analysis, volumetric analysis, detection of radical in salt, and acidimetry. Surely you have to discuss, you have to know about it, that quantitative analysis is the analysis in which we measure the quantity. We measure certain quantity, but we are not detecting any species, chemical species. So which out of the following is not a quantitative analysis? Here, gravimetric analysis. Gravimetric analysis measures the mass or weight of substance. So surely it is quantitative analysis. And volumetric analysis measures the volume of reagent, volume of the solution. So measurement of volume is definitely a quantitative analysis. And similarly, detection of radical in salt. For example, if you have sodium chloride salt, then you identify which is cation, basic radical, and which is anion, acid radical. So this is just the identification or detection of radical in salt, but not the calculating the amount of radicals or amount of cations or anions. Therefore, the detection of radical in salt is not the quantitative analysis, and it is the qualitative analysis. Similarly, acidimetry, standard, with the help of standard acid, you measure the concentration of base, unknown base. So that is acidimetry. Acidimetry is a part of volumetric analysis, and it definitely is a quantitative analysis. So our answer is detection of radical in a salt. Detection of radical in salt, or detection of basic radical or acid radical in salt, is the example of not quantitative analysis, but it is qualitative analysis. So this is the first question that we have discussed today. Now let us go to second MCQs, 7 MCQs that you may be asked in the exam. So second MCQ is, which of the following quantity is concerned in gravimetric analysis? So number 2, which of the following quantity is concerned in gravimetric analysis? Which of the following quantity is concerned in gravimetric analysis? Definitely we have 4 options here. Which of the following quantity is concerned in gravimetric analysis? If you are studying gravimetric analysis, you must know that which of the following quantity is concerned there. So Number A option we have volume, number B is mass, number C is density, and number D is temperature. Definitely, if you are reading the gravimetric analysis, then gravimetric means measurement of mass or measurement of weight of the certain substance, and it does not measure exactly the volume, density, and temperature. So it directly measures the mass of substance by the stoichiometric calculation from the reaction. So definitely the answer is mass, but it's not the volume, density, and temperature. So gravimetric, if you talk about gravimetric analysis, you have to measure the mass of substance from the reaction, from the stoichiometric ratio of the reactions. So gravimetric analysis is mainly concerned to mass of the substance. So now we go to next number third MCQs. Let us see number third MCQs. Which of the following apparatus is used for gravimetric analysis? So which of the following apparatus is used for the gravimetric analysis? Number A is burette, number B is pipette, number C, burette and pipette we have, and then number C we have volumetric flask. Number D we have crucible. Which of the following apparatus is only used for gravimetric analysis? Which of the following apparatus is only used for the gravimetric analysis? So if you know about the gravimetric analysis, you might have seen about the different types of apparatus used there. So out of 4 options we have, which of the following is used in gravimetric analysis only? So gravimetric analysis should in gravimetric analysis there we should form the precipitate, and precipitate should be dried and the mass of precipitate should be taken. And during this process, important apparatus that we will use is crucible. Crucible is used there. But if you are doing titration or volumetric analysis, there we use burette, pipette, and volumetric analysis, because there we have to measure the volume. So which of the following apparatus is only used for gravimetric analysis? The answer is crucible. Number D, crucible is the answer. A crucible is a small apparatus in which we put precipitate and we dry it. So we sometimes ignite the precipitate also. This is crucible. So the apparatus which is only used for the gravimetric analysis is crucible. This is number third. So let us go to number 4. Let us go to number 4. Which of the following relationship shows? Number 4. Let us go to number 4. The relationship between equivalent weight, atomic mass. The relationship between equivalent mass and atomic mass of an element is we have option here. The relationship between equivalent mass and atomic mass of an element is we have option, suppose A equals to E into V, number B, E equals to A upon V, number C we have V equals to E into A, and number D we have none of above. So if you are going to find the relationship between equivalent mass and atomic mass, which is the correct relationship? So we know that equivalent mass is equal to atomic mass by valency. Suppose that if you have magnesium, equivalent mass of magnesium, then magnesium has got atomic mass 24 AMU and it has got valency 2. So 12 is the equivalent mass of magnesium. So surely the answer is equivalent mass equals to atomic mass by valency. So this relationship you can easily use to find the equivalent mass from the atomic mass of element if you have valency. So this relation also is useful to say that equivalent mass is variable, but atomic mass is not. For example, if copper has got atomic mass, certain amount of atomic mass, and it has got valency 1 and 2, therefore equivalent mass of copper in valency 1 state is different than that of equivalent mass of copper in valency 2 state. So this relationship is very useful to know about the equivalent mass and the atomic mass relationship. So this number 4 is related to the relationship between equivalent mass and atomic mass. So let us see next question, number 5 question. Let's go to number 5 questions. The equivalent mass of anhydrous sodium carbonate is the equivalent mass of anhydrous sodium carbonate. Anhydrous sodium carbonate is, so what is the equivalent mass of anhydrous sodium carbonate? We have option here. So number A option is 106 and number B option we have is 63. Number C we have 53 and next is number D is 126. So we are concerned to equivalent mass of anhydrous sodium carbonate. So anhydrous sodium carbonate means it doesn't have any kind of water of crystallization, so it's just sodium carbonate. And sodium carbonate, we may consider sodium carbonate as a salt. In case of salt, equivalent mass of salt equals to molecular mass upon total charge on cation. So if you have sodium carbonate, you know sodium carbonate when ionizes, it gives 2 sodium plus carbonate ion. So cation has got 2 positive charge, therefore molecular mass of sodium carbonate is 106 and total cationic charge is 2. So divided by 2 and it's a 53. So equivalent mass of sodium carbonate, anhydrous sodium carbonate is 53, which is very popular in volumetric analysis because anhydrous sodium carbonate is primary standard substance and it can be used to find out the concentration of different kinds of acids by preparing the standard solution of sodium carbonate in alkalimetry. So sodium carbonate is often used in alkalimetry to find out the concentration of unknown acids. Therefore, sodium carbonate equivalent mass is very popular in acidimetry and alkalimetry chapter or volumetric analysis chapter. Therefore, equivalent mass of sodium carbonate is 53. We can calculate the equivalent mass of sodium carbonate in this way. So we have number 5 now. Now let's go to number 6. Now let's go to number 6 multiple choice questions. In number 6 you have given a reaction. We have a reaction 2 sodium hydroxide plus phosphoric acid. And then we have Na2SPO4 plus water. 2 water. So this kind of reaction we have, and what is the equivalent mass of phosphoric acid in this reaction? Equivalent mass of phosphoric acid in reaction is, in this reaction what is the equivalent mass of phosphoric acid? We have option here. We have option molecular mass, number B molecular mass upon 1, molecular mass upon 2, molecular mass upon 3, D. It is equal to molecular mass upon 2, molecular mass upon 3, and it's just molecular mass upon 1, molecular mass or molecular mass upon 2, molecular mass upon 3, and it's equal to molecular mass divided by 4. So what is the equivalent mass of phosphoric acid? You know that phosphoric acid is an acid, and acid has got equivalent mass equals to molecular mass upon basicity. So basicity is number of hydrogen ion that it produces, as 3PO4 gives 3S plus and PO4 minus minus minus. It has got 3 basicity as it produces 3 replaceable hydrogen. as it has three replaceable hydrogen. But the molecular mass of H3PO4 divided by which number depends upon the reaction. If you see in a reaction, the base, the metallic part of base has displaced only two hydrogens from the phosphoric acid. Here you can see one hydrogen is still left and two hydrogen are only left displaced. So number of displaced hydrogen is 2. Therefore, the equivalent mass equals to molecular mass upon 2 here, as displaced hydrogen is only 2 here. So when you are going to find the equivalent mass of phosphoric acid, then you must be concerned that how many replaceable hydrogens are used there in the reaction. For example, in our reaction we have seen that only 2 hydrogens are being displaced. So we can easily say that the equivalent mass of phosphoric acid is molecular mass by 2, though it has got 3 replaceable hydrogen. So you are concerned to reaction, and you must be careful to see in the reaction that how many hydrogens are displaced from the reaction, from the acid. So our answer is molecular mass upon 2. Okay, now we go to next question. Number 7. Mass of solvent is necessary to calculate. Mass of solvent is necessary to calculate normality, B, molarity, C, formality, or number D is molality. To calculate the concentration of a solution, which of the following, which out of the 4 quantity needs mass of solvent? Mass of solvent in kg or mass of solvent in gram? In which term calculation there is mass of solvent necessary? So you must see that normality is equals to number of gram equivalent upon volume in liter, volume of solution in liter. So there is no any concern concerning about the solvent mass of solvent. So normality is not the answer. So if you see molarity, then molarity is number of moles of solute divided by volume of solution in liter. So we are even not concerned to mass of solvent there. Formality is definitely number of formula mass upon number of formula mass, or we can say that mass of solute divided by formula mass divided by volume of solution in liter. So here in formality case also there is no nature of any kinds of mass of solvent. Therefore, in molality, when we are going to calculate the molality, then molality small m, we represent molality by small m. We are concerned to mass of solvent because this is number of moles of solute divided by mass of solvent in kg. So molality is the concentration term in which we are mainly concerned to mass of solvent. So you need to know the mass of solvent if you are going to calculate the molality. So molality is the concentration term in which you are mainly concerned to mass of solvent. Okay, this is number 7. Now we go to number 8. Today we are going to discuss about some MCQs, some basic MCQs of volumetric analysis. Now we are going to number 8. Okay, number 8. For ionic salt solution, concentration is best expressed in, for ionic salt solution, for example sodium chloride solution or any kind of ionic salt solution, concentration is best expressed in normality, or molarity or molality or formality. So which of the following concentration term is mainly used for the ionic salt solution? For ionic salt solution, ionic salt solution means when ionic compounds are dissolving in solution state, then there we will not have any molecule, but there will be ions. So if you are going to dissolve sodium chloride in water, then you never get existence of sodium chloride molecule, but you will get sodium plus and chloride ion there. So it is better to express ionic mass or formula mass of ionic compounds rather to say molecular mass. So for this kind of compounds, it's better to express the concentration term in case of formality, and formality is equals to gram of solute divided by formula mass of ionic compounds. For example, sodium plus chloride ion, mass of sodium plus and mass of chloride ions, formula mass of ionic compounds divided by volume of solution in liter. So if you are going to prepare the ionic compound solution of ionic compounds, then at that time it is better to express the concentration in terms of formality, because formality gives the calculation of formula mass of ionic compounds, gram of solute divided by formula mass of ionic compounds, which is divided by volume of solution in liter. So there is no existence of molecule, and there is no any concern about the molecular mass, because molarity needs molecular mass, and even normality needs equivalent mass, which is calculated from the molecular mass. Therefore, normality, molarity, and molality are not mainly concerned for ionic compound, and it is more exact to express the concentration of ionic ionic compound solution in terms of formality. So answer is what? Formality. Definitely formality is a concentration term used for ionic compound solution. Okay, this is about number 8, and now we are going to number 9. So let us see number 9 questions. Okay, let us see in number 9. In number 9, hardness of water is better expressed in hardness of water is better expressed in normality, B molarity, C molality, and D ppb, parts per billion. So if you are concerned to hardness of water, water has got two kind of hardness: permanent hardness and temporary hardness. So if you are going to estimate the ions or estimate the concentration of the species which causes the hardness of water, at that time the ions will be in very less amount, less amount. So at that time, if solute is in very less amount, then at that time normality, molarity, and molality are not the good way to express the concentration, but we can express the hardness of water in terms of ppb, parts per billion. Okay, so this ppb is the concentration term in which we express the hardness of water. And the ppb is the way to express the concentration in this way. ppb equals to parts per billion equals to mass of solute in gram divided by mass of solution in gram into 10 to the power 9. So it is the concentration term to be used for estimation of the micro or trace element in the solution. So hardness of water, and the chemical species which causes hardness of water is definitely in minimum amount, very less amount, and that is better expressed in parts per billion or parts per million. So normality, molarity, and molality are not the better concentration term, but parts per billion is the better concentration term to express hardness of water. So you might have heard about the concentration of arsenic in water is that much ppb, and so if you want to calculate the trace amount, very less amount chemical species in solution, then you should better express this concentration term as ppb, parts per billion. So this is number 9. Now we go to number 10. Okay, let us see number 10 MCQs. Okay, which of the following is not the criteria of which of the following compound is primary standard substance? Which of the following compound is a primary standard substance? Which of the following compound is primary standard substance? You have option here. Which of the following is a primary standard substance? And you have the option there: potassium permanganate, potassium permanganate. And number B, you have silver nitrate. Number C, you have sodium hydroxide. And number D, you have anhydrous sodium carbonate. Anhydrous sodium carbonate. Okay, you are here concerned to primary standard substance. Which of the following substance is a primary standard substance? Do you know about primary standard substance? Definitely, primary standard substance are those substances which when we take mass and make solution, and the concentration will not be changed, and the substance should be stable in heat, light, atmosphere, and it should not absorb or eliminate the water of crystallization. So molecules should be stable in solution state as well as in solid state. It should not be toxic, and it should be easily available. Like these all criteria we have for a primary standard substance. For example, if you have potassium permanganate, potassium permanganate is the light sensitive molecule, and potassium permanganate gets decomposed into different types of substance if you have light or heat. So this potassium permanganate is not a stable compound to be used as primary standard substance. Silver nitrate. If you are talking about the silver nitrate, then silver nitrate is definitely light sensitive molecule. In the presence of light, it decomposes into different different other substances. And silver nitrate solution is always wrapped with the carbon paper or black paper, because silver nitrate gets decomposed when there is presence of water. Similarly, sodium hydroxide. Sodium hydroxide is it's a very common base used in the lab, and sodium hydroxide is a hygroscopic substance. Hygroscopic substance because it absorbs the water molecules from the atmosphere. So the sodium hydroxide cannot remain as it is when you make the solution. So you cannot prepare the standard solution of potassium permanganate, silver nitrate, and sodium hydroxide as a primary standard substance. Therefore, anhydrous sodium carbonate is only the substance that can be used as a primary standard substance, because it is not absorbing any water and is stable. So anhydrous sodium carbonate is the example of primary standard substance. So you will have two kind of substance when you prepare the solution. One, you have primary standard solution, and other will have secondary standard solution. Primary standard solutions are prepared from the primary standard substance. So for these multiple choice questions, you must know the criteria of primary standard substance. Okay, now we are going to number 11. So let us see number 11. In number 11, we have one important question regarding indicator. So indicator indicates the point by changing the color of itself. Indicator indicates the point. Which of the following point is indicated by an indicator in titration? When you do titration, then at that time, which of the following point is indicated by the indicator? Indicator is a chemical substance that changes color of itself after when the two reacting substances are completely reacted. So A is equivalence point. Equivalence point. Number B. Number B is theoretical endpoint. Theoretical endpoint. Number C is stoichiometric point. Stoichiometric point. And number D is all of above. So you know that we use the indicator in titration, and indicator is the chemical substance that indicate the equivalence point when two reacting substances taken in a burette and conical flask completely react to each other. Then at that time the reaction has been completed is indicated by the indicator. That point in which two reacting substances taken in a burette and conical flask exactly neutralize to each other is called equivalence point. And definitely equivalence point is also called theoretical endpoint and stoichiometric point. So these 3 points are similar, so we have the option number D, all of above. So indicator is used in a titration to indicate equivalence point or theoretical endpoint or stoichiometric point. So the answer is number D, because these all 3 terms are synonymous. Now we go to number 12. Which of the following is not the acid-base indicator? Acid-base indicator. Which of the following is not the acid-base indicator? We have option here. Number A is phenolphthalein. Phenolphthalein. Number B is methyl orange. Number C, we have litmus paper. And number D is starch. So you have acid-base indicator. I mean, acid and base can be distinguished by or the substance which gives different color in acid and base is the indicator, acid-base indicator. And phenolphthalein definitely is the acid-base indicator because in base it gives pink color, and in acid it doesn't have any color; it's colorless. Similarly, methyl orange is the orange color in definitely basic range, and in acidic range it will change its color. So litmus paper is also definitely acid base indicator because it is used to indicate whether it is acid or base, because litmus paper will have different color in acid and base. But definitely starch is a substance that is used in iodometric titration because starch form complex with iodine and it gives blue. So it is definitely used for iodometric titration and not for acid base indicator. It's a redox titration. Okay, redox titration, or we call iodometric or iodimetric titration. In such kind of titration we can use starch as an indicator. So when reaction is completed, starch forms a complex with iron and it gives a blue color, and indicator indicates the endpoint. Indicator indicates the equivalence point in the redox titration. Therefore here starch is a redox indicator, but not the acid base indicator. But other 3 are the acid base indicator that can be used for acidimetry and alkalimetry or acid base titration. So is a number 12. Now we go to number 13. Let us see number 13. In number 13 we are going to discuss about one more MCQs. In number 13, okay, acidimetry uses standard base. Number B, standard acid. And number C, acidimetry is an experiment, is an acid base titration which uses standard base, standard acid. Number C, both A and B. and number D, none of above. Okay, you know about acidimetry, and acidimetry is the titration experiment in which standard acid is used to determine the concentration of unknown base in the titration. So acidimetry means acid, with the help of acid we measure the concentration of base, therefore we use here standard acid in acidimetry. If you have alkalimetry, you know, definitely in alkalimetry you use the standard base, and in acidimetry you use the standard acid for the titration to measure the unknown concentration of base. So acidimetry definitely use standard acid. Okay, now we go to number 14. Number 14 MCQs. In the titration of KMnO4 with oxalic acid solution, which is standard oxalic acid, if you are going to find the concentration of potassium permanganate with the help of standard oxalic acid solution, the titration is the titration is number A, acid base titration. Number B is complexometric titration. Number C is you have redox titration. And number D you have precipitation titration. Okay, you have different kinds of titration method. You are going to know the name of different kinds of titrating method. In the titration of potassium permanganate and oxalic acid, you know potassium permanganate is oxidizing agent and oxalic acid is reducing agent. Whenever there is a reaction between oxidizing agent and reducing agent, and that we use that kind of reaction, if we use in the titration, this is definitely called redox titration. And acid base titration only uses the acid and base as a reacting substance. Complexometric titration we have like EDTA, complexing agent. For example, if you want to estimate the calcium ion in water, then you use EDTA, and EDTA pumps the complex with the calcium, that gives calcium EDTA, and we measure the calcium EDTA by the titration. In this way we can use the complexometric titration for the estimation of different kind of substance. Precipitation titration, we can make the precipitate in the titration reaction. So therefore our reaction between KMnO4, potassium permanganate, and H2C2O4 in acidic medium, it is the example of redox titration, because here it is acting as oxidizing agent and here oxalic acid acts as reducing agent. So the reaction between oxidizing agent and reducing agent is definitely called redox reaction, and the titration on which redox reaction is used, that kind of titration is called redox titration. So definitely the titration between potassium permanganate and oxalic acid solution is an example of redox titration. Okay, this is number 14. Now let us go to number 15. Okay, in number 15, we are going to know about the reagents of solution whose concentration is the reagent solution of known concentration. The reagent solution of known concentration is, in the titration you use one of the solution as a known solution and other as unknown solution. The reagent solution of known concentration is called, so you can call it as, the reagent whose concentration is known as titrated. Number B is non-standard solution. And in number C you call it as titrant, and number D is indicator. So the reagent solution whose concentration is known is definitely called as standard solution, and the solution whose concentration is known as known concentration is known as titrant. Titrant is the substance whose concentration is unknown during titration, and titrant is the substance whose concentration is known. So indicate is definitely not a reagent because it is a third substance that is used to indicate the equivalence point. It is not definitely non-standard solution. And titrant, we have two options, but titrant is the term that is used for the concentration of used for the reagent solution that is of known concentration. So the answer is titrant. So you must know about the term titrant and titrant in the volumetric analysis. This is number 15. Okay, now we go to number 16. In number 16, we definitely know about the normality equation. Normality equation is number A, B1 N2 equals to B2 N1. B1 N1 equals to B2 N2. C, B1 by N1 equals to B2 by N2. Number D, B1 B2 equals to N1 N2. Which of the following is the normality equation? You know normality equation. Normality equation is the basic principle of law of chemical equivalent, and gram equivalent of A equals to gram equivalent of B. Gram equivalent is definitely normality into volume in liter. For example, if for A you say 1, then N1 B1 equals to gram equivalent of B equals to normality of B, that is N2, into volume in liter B2. So definitely law of gram equivalent says that the normality equation is B1 N1 equals to B2 N2. So definitely the answer is B, B1 N1 equals to B2 N2 is the normality equation. So this is number 16, and let's go to number 17 now. So in number 17, the molarity of pure water is for example, we have molarity of pure water is 100 molar. Number B, this is 50 molar, and number C, this is 18 molar, and number D, we have 55.6 molar. So what is the molarity of pure water? Can you calculate the molarity of pure water? Definitely we can calculate. Molarity of pure water is calculated by molarity equals to gram of solute divided by volume of solution in liter. So you know the density of pure water. Density of pure water equals to 1 gram per cc. Therefore, pure water has got 1 gram per cc. 1 ml has got mass 1 cc has got mass 1 gram. Therefore, molarity equals to 1 divided by volume of solution is 1 cc divided by 1000. That you have to divide by 18 for changing into mole. 1 divided by 18 is the mole of water. 1 gram changed into mole is equal to 1 upon 18, and per cc, 1 cc is divided by 1000, then you change into liter. Therefore 1000 by 18 molar, that is 55.6 molar is the molarity of pure water. So the answer is number D. So the pure water has got molarity equals to 55.6. So this is number 17, and now let's go to number 18. Let us see in number 18 the normality of 1 molar H2SO4. The normality of 1 molar H2SO4 is number A option you have 1, number B option you have 2, number C option you have 0.5, and number D you have option D 10. So what is the normality of 1 molar H2SO4? It's a very simple questions. Normality and molarity relation, you must know it. So you know normality equals to normality equals to molarity into basicity. This is the relation, you know. So normality equals to molarity into basicity. Molarity is 1 we have, and basicity of sulfuric acid is definitely 2, as it has got 2 displaceable hydrogen in sulfuric acid. So it's a 2 normal. So normality of any kind of acid, if you want to find sorry, from molarity, then you must have the relationship that normality equals to molarity into basicity, because you know, basicity, normality equals to molarity into basicity is molecular mass upon equivalent mass. That also you can use, whatever you use, the normality is 2 normal, so answer is B. So you can easily convert the normality into molarity or molarity into normality if you have the relationship. So this is number 18. And finally we go to number 19. Okay, in number 19 we have 200 ml of HCl, 200 ml of HCl of 2 normal is neutralized by 200 ml of the normal sodium hydroxide. So option A is, you know, 1 normal, number B is 0.5 normal, number C is 2 normal, and number D is 3 normal. So you can easily find out it by normality equation. B1N1 equals to B2N2. So you have B1 200 ml and N1 equals to 2, and B2 you have 200 again, and N2 equals to what? Therefore N2 equals to 2 normal. Definitely you can find out it by normality of any ways, that is completely neutralized by the 200 ml of HCl of 2 normal, that has 2 normal. Or you can also use that equal volume if you have acid and base. If equal volume of acid and base you have, then equal normality there must be, because gram equivalent neutralize is always equal, and that law of chemical equivalence also say that equal volume of acid and base are neutralized in equal concentration or equal normality. So you can find out the answer as 2 normality. So it's very simple questions, but it's basic questions in volumetric analysis. Okay, finally we go to number 20, the last questions of today's class. So let's go to number 20. In number 20, in the titration of KMnO4 and oxalic acid, the indicator is number A, you have methyl orange, number B, phenolphthalein, and number C, you have got oxalic acid, number D is KMnO4. Okay, out of all, you know, this is the titration of oxidizing agent and reducing agent. This is redox titration, and redox methyl orange acid base titration. So this is not the answer, because this is acid base titration, acid base indicator in the titration. Phenolphthalein is also acid base indicator, and that is also not the answer, because it is a redox titration. And oxalic acid itself is reducing agent, and it doesn't have color, so it cannot be used as indicator. But KMnO4, you know, when KMnO4 and sulfuric acid along with oxalic acid are reacted to each other, then potassium permanganate pink color gets colorless, gets changed into colorless and colorless. But at the equivalence point, you know, after when the potassium permanganate and oxalic acid are completely reacted, then extra drop of potassium permanganate that you drop from the butyrate will give the pink color in the solution, and therefore KMnO4 itself acts as indicator. This is called, you know, self indicator. So in this case, the self indicator KMnO4 is used as an indicator. So friends, today I have discussed 20 MCQs, basic MCQs from the volumetric analysis. Surely I think that you enjoy these MCQs, basic MCQs. So if you are reading the volumetric analysis, then you must know these basic MCQs at least then you can go to more and more difficult type of MCQs. So definitely, if you enjoy my videos, then subscribe my channel for more videos. For today, let us say bye bye to everybody. Thank you.